Get started. Good morning, everyone. We are Team G.R.A.S.P, the grip rectifying assistive sensor pen, and we're excited to share with all of you the updates to our assistive design project. To go to the next slide. To start with a brief recap of our project, our group is looking at the difficulties with proper handwriting posture most commonly seen in young children. Although it comes easy to many, the fine motor skills used in good handwriting can be difficult to learn and master at a preschool to kindergarten level. We propose a solution of creating an assistive device that is able to do two things. The first is to measure three key components to proper handwriting posture, those being finger positioning, finger to pen force, and pen to paper force. We were able to identify these areas through the combination of heavy literature review, as well as speaking to different teachers and occupational therapists. So we are confident that studying these areas will be important when it comes to handwriting. The second part is based off of those measurements. We want our device to be able to record the data and report back to the user with live feedback with the hopes of helping them with their writing. We were successfully able to build and test this prototype, and we are excited to take you through that process today. We'll start with the design of the model itself, to which I'll pass things over to Suresh on the next slide.
Hi guys. So our goal in terms of design is to make it more modular and compatible with most of the pen, but still keep it simple and make it easy for us to access the circuit or the sensors that is present in the pen. Also, it should be easy for us to swap the components in case of a failure or a damage in the sensors. Next slide. Previous slide. Initially, we planned to design our own pen from the scratch, but it seemed modifying an existing pen would save us more time and reduce our overall cost of the product. Next slide. We have decided to go with the tripod grip since it has the most efficient grip for writing, as it helps us achieve finer level of control. There are two components in our pen. The first one is the finger positioning component, and the second one is the hub, which consists of the IMU and the pen tip pressure sensors. The finger positioning component makes sure all the fingers are held in the correct position and checks if the required amount of pressure is applied on the pen. It also ensures all the force is focused on the pressure sensor, and this is achieved by the finger pressure pads. Next slide. The second component, which is the hub, consists of the IMU and the pressure tip sensor, and we have a spring at the tip of the pen which pushes the ink cartridge back in order to apply a constant force on the pen tip pressure sensor. Now Jack will explain the integration of the sensors with the pen.
So hey everyone, I'll be talking about the resulting prototype that we developed and the components that it uses. So at a high level, we've integrated the 3D printed parts that we just mentioned with a modified pen base to create a kind of exoskeleton for our device. This skeleton, we've primarily utilized force variable resistors and an 8 degree of freedom IMU to sense the environment around it. Now, these force variable resistors are exactly that. They are resistors that change their value based on how much pressure is applied to them individually. This concept is utilized by placing them in series with another resistor to create a voltage divider that varies its voltage based on how much pressure is applied to the force variable resistor. We could then read this value into our MCU as an analog input. And this is kind of the basis of how we sense the user interacting with the device. Next slide, please. So really quick, I just like to show a video outlining these components on our device. We can play the video.
I'm going to go over some points of interest on it just to explain some of the designs that we've done. The first one is these force variable resistors in the grip part here, which we can see. Here's a standalone version of it. We have some grooves for the finger location in addition to these displacement pads, as you can see them coming down. That's to evenly distribute the force onto our sensors underneath the fingers of the device. In addition, another point of interest is this back housing that we have. This holds the IMU, which can be seen here. It's fixed so that we only need to calibrate it once, and then we have a reference point for the rest of the device. And this other more sensitive force variable resistor, which goes in the back of the housing here, which measures the pressure force between this back housing and this internal cartridge, the one that holds the ink. So that's how we measure this pen tip force.
Okay, next slide, please. Okay, so I'm going to go into the main concepts that we utilized. As you can see here on the left, we have the wiring diagram of the device. The main brains of this schematic is a dev board that we've selected named the ESP32 Room 32D. This is a more modern Node MCU dev board, which was ideal for our prototype as it has a wide array of analog to digital input pins, which allow us to read that voltage that I was talking about before. The two sensors that you see on the right there are the two different types of variable resistors we use. There's the SEN 09673 and the DF940. The main difference between these two is that the SEN 09673 were the ones that we used for the finger tip force. They have a wider range of operation and an upper resistance of about 10 mega ohms, and it's in series with about a 4.7 kilo ohm resistor. On the other hand, the DF940 has a smaller range of operation, but it is more consistent and precise in its measurements. It has an upward resistance of about 1 mega ohm and is in series with a 10 kilo ohm resistor. The last device there on the right is the IMU that we chose, which is the GY521. It has a built-in MCU called the MPU 6050. It boasts a small form factor, which was ideal for integrating into our device. And in addition, it was very easily calibrated with the acceleration due to gravity so that we can measure the offset of the pen to calculate a tilt angle for the user. Finally, the last thing to mention is that our microcontroller has a ESP32 Wi-Fi module, which Smriti will talk about in the next slide.
Thanks, Jack. So ESP32 is a Wi-Fi module that can implement TCP/IP among other protocols. It can act as both client and server. In our application, we use ESP32 as the client and ThinkSpeak as the server. So ESP32 reads sensor values in form of analog readings, passes them into the required format, which can be MQTT, JSON, or CSV, and posts these values to the ThinkSpeak server using unique write API keys. Each sensor has a field allotted to it where the values are plotted against time. All this data is stored in a unique private channel, which can be made public if required. Next slide. So ThinkSpeak is an IoT analytics platform that allows you to visualize and analyze live data. So the reason we chose ThinkSpeak is that it improves accessibility, which is the most important factor for any assistive technology. The occupational therapist does not have to be present in person to analyze the child's handwriting and can go back to the data at a later time to analyze it and come up with better suggestions or methods to improve the child's handwriting. Another advantage of using ThinkSpeak is that it allows you to collaborate with multiple apps or softwares like MATLAB and social media platforms, which gives you a variety of options to visualize, analyze, and share the data. Next slide, please. Now I'm going to talk about how we tested our product. So 6 of us wrote the same piece of information to maintain consistency with both our left and right hand. This was done to compare good handwriting to relatively bad handwriting. So as people wrote, the data was read by ESP32 and simultaneously published to ThinkSpeak, and there it was visualized. So 2 issues which we ran into while testing was that one is that ThinkSpeak can update only, the free version of ThinkSpeak can update only 15 seconds, which is not enough. So we did come around a workaround and we were able to bring it down to an update per second, but that is still not fast enough. So the solution to that would be getting the paid version of ThinkSpeak where it can update much more faster. And the second issue is that we found it really difficult to write with our left hand. So we wrote only one sentence compared to the right hand. So now I'll hand it over to Rushi for explaining the results.
Okay, thanks, Smriti. So as she said, well, we wrote with our right and left hand, and I'm just going to go over some of the key results from all that testing. So firstly, what you see on the screen are some handwriting samples from the left and the right hand. And it's quite obvious that we all struggle quite a bit while writing with our left weaker hand. The purpose of this little experiment was to mimic a non-proficient writer, in our case, a child, and to analyze the resulting data to see if we can figure out what's going on actually with all of this. So moving on to the next slide. What's up on the screen are just graphs of mean grip force, which we get from the grip sensors over time. And looking at them just on the face of it, you can see that the force variability is higher for the right hand than the left hand. Now, these results are an indicator that grip variation is an indicator of better legibility and speed. Now, our brain is an extremely sophisticated controller, which we take for granted. And what it's doing here is regulating fine motor aspects, which are missing in the left side or the weaker side of a predominantly right-handed person. And so basically, this hypothesis is matching with one of the results from our research of a 2010 study on grip force variability and its effects on children's handwriting. Now, while most standardized handwriting tests are going to subjectively measure handwriting and attach a score to it, we provide an objective measure to handwriting, which is the sensor data and the grip and the axial components and the inclination angle from the IMUs. And even a study from 2021 published in the Journal of Assistive Technology said that the data on grip force and normal force can be mined to extract some insights for the occupational therapist to allow for a more well-informed method of intervention. So without taking much of the time, I'm going to move on to the next slide. And just briefly, by this point, you might be like wondering, all of this sounds great, but I want to see the actual pen that you're talking about. But hold on, before I actually play the video, I'm going to demonstrate some of the function, how the pen functions by just explaining the logic that goes behind the pen's handwriting assessment algorithm. So these are the protocols. So basically, when you boot up the pen, it starts calibrating, jumps into this initialization mode, and it will continue blinking purple, as you can see in that block, until the user's fingers are in the correct position and applying the appropriate amount of grip, at which point it's going to turn blue. At that point, the pen is the axial forces are collected and normalized by using the angle of inclination, which you can see in the bottom left. So you get the normal component. This normal component is basically not well regulated by children, which detrimentally affects their handwriting. Which we've spoken to one of the occupational therapists, and they have said that this is one of the key components which they like to regulate. So we used sensors to kind of like a red light to indicate that it's bad when you push down in excess. So without just going into details of that, let's just see it in action on the next slide, please. So as you can see at this point, it's going to be calibrating, and it goes into this initialization phase where it blinks, and this blinking indicates that the user is supposed to put their hands in the correct position. Once the correct position is acquired, it turns blue or stops blinking, which now you can start writing. And when you start writing and you're writing in the correct range or with the correct surface pressure, it's going to be green. And once the user starts applying an excess force, it's going to go red. And along with this, there's also a vibration motor, which is going to vibrate in proportion to the amount of actual force being put down. I don't know if you can hear it, but you can see that the vibration motor is going to buzz more. With that, that is just the demo of our project. And Mayur will now go over what these results actually mean for our team.
Thank you, Rishi. So now I'd like to conclude the presentation. To conclude, I'd like to recap the presentation. Our aim was to give live feedback to user while writing. We had 3 parameters which are responsible for how the person holds and interacts with the pen while writing: the pen paper force, the finger pen force, and the finger positioning, which we were able to successfully measure using the force sensors, the IMU, and the interface with meaningful outputs like LED and vibration. We were able to get real-time feedback which can be shared with teachers and occupational therapists to help them better understand where a student is making a mistake and cater an intervention specific to the individual needs. The design is also simple and intuitive. because the feedbacks are set in such a way that they are easily understandable. Like red light means bad pressure, and more buzzing is like pen pushing back at you, telling you to reduce the grasping force. Now let's go over to the future scope. In future, we'd like to implement handwriting recognition with the pen, which will give us an accuracy for the handwriting for target goal of how smooth the user wants to be, using a supervised learning model. Also, we can make the pencil more ergonomic by eliminating the wires and placing the LEDs on the pencil to have a much more interactive experience. In addition to that, we can also implement some subtle vibration for incorrect postures along with LEDs. Or if the person is unable to send some small vibrations, we can use auditory feedback in the form of the sound that is proportional to the volume to the amount of pressure which the children might apply on the pen in case of excessive forces being used. Finally, we'd like to test the pen with the kids to see how they can improve the handwriting with the G.R.A.S.P pen. This concludes our presentation, and now we are up for any questions you guys might have. Thank you.
Great, thank you very much. Those you guys reported some very exciting results, particularly there. I believe it was Rushi who was talking about those graphs. I think there was like recorded force measurements, right? If I'm not.
Yeah, if you can go back to that site, please, Mayur.
Yeah, if you go there. This is quite intriguing because that shows the level of manipulability and force closure control you have on the right hand versus your left hand, and that's a very, very interesting. I know you guys have been busy with putting together all this, but it would be exciting to share this result with some of the people that you kind of reached out to before the. Have you been able to share these results with some of those people to see what they say?
Yeah, definitely. When I go home for Christmas break, I'm definitely going to share this presentation and show these results to the occupational therapist and the teacher that we spoke with, because originally this whole project was based on an identified kindergarten girl from a school in my hometown. So I think this would be really good information to share with them and see what they make of this kind of data.
Absolutely. Sure. I think, Austin, that would be a great idea. And I'm personally interested to see what comes out of this, because I mean, just this slide itself might have tons of interesting information for people who really know about, the details of this problem that kids face. And certainly having this device available to them, perhaps that better helps them to, systematically look into this problem. Great presentation, great collaboration between the team members, and great demo. I was quite happy to see that. Let's see if the class has any question from your group, and any questions from the class.
Can I ask one more question?
Yes, Harry, go ahead.
Yeah, as I can see, your pen is has many wires setting out. Do you have plans of incorporating all those units into a single pen that can be portable and can be distributed around the students, or do you plan to leave the pen in a lab or in the into the mentor that can be practiced using by the children?
So that's a great question. A big issue with prototyping is the modularity of the device. A big thing was we were changing out designs pretty consistently, and we wanted accessibility to these sensors while we were testing it. So this is primarily the prototype version of this device. If we were to finalize the product, we would refine it significantly, and ideally, print some integrated PCBs, some integrated wiring, have our own model for it. Really reduce the form factor of the entire device so that it's more of a standalone product rather than, it kind of looks like a hodgepodge of things thrown together right now. So ideally we would reduce the size of things. We would integrate all the wires into the inside and hide all the electronics, especially if it's something that's going to be used with children. It was just for this project, it was something that we kind of had to keep accessibility to the individual sensors and the wiring and everything like that.
Yeah, I can see that. So you are actually going to incorporate all those things into a single pen, right?
Yeah, if that was something that
Okay, I
we
see, I
were to move forward with, yeah.
That was a great idea. Thank you.
Yeah, just to add to Jack's comments, that's the prototyping stage for them, Harry, and they were more concerned about functionality and proof of concept than the cosmetic stuff. So that's something that next they are going to look into. It would be cool to see if this thing, for example, I don't know, can pairs up with your smartphone or with your, I don't know, Samsung Watch or Apple Watch to sort of record all this information. No, I think overall it's quite promising and quite interesting to see that with some really the sensors and the components that you use, they are really basic components, and when all they come together, you come up with such a powerful tool that can help reveal some important answers to some like perplexing questions. But no, great job, great presentation, great demo, as I said, and let's move on to the next team. Thank you guys, thanks for the great work, and I'm looking forward to hear from you, Austin, and how things unfold. Okay.
Thank you, Professor.
Yeah,
Thank you, Professor.
great.
Thank you.
Thank you, guys. So who is presenting next? Please take the stage and let's move on to the next presentation.